I just wanted to go over a few of the things that sort of cropped up after lectures today and some of the questions that people were asking, and also to kind of go through maybe again the two examples that I did on the board, and also a couple of other additional examples which act in addition to the further examples that I've given in the videos in the post on the blog page. Okay, so one of the things that came up after the lecture was this, that in the lecture I said we sort of had the question of how many ways can I order the letters B, 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 W, W. Okay, so that was for sort of black. So you have 3 black letters and 2 white letters, and how many ways can you rearrange those? Okay, so firstly, well, there's 10 of them, and I've explicitly written them out over here. So notice what I've done is sort of try to keep the B's as far left as possible, and when I can't keep them any further left, I just kind of move one of the B's over. Okay, so we've got B, 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 W, W, and I go, well, okay, I'm going to have to move this B, so the next one would be B, B, W, B, and I go, oh, okay, I don't really want to move this one before I've moved this one, so I move this one over, and so forth. And then when I really can't move the rightmost B, I begin to move the next most rightmost B, and keep on going. Okay, and there you can see there's 10 outcomes. Okay, there are 10 possibilities for combining these 3 letters B and 2 letters W. All right. Now, what I mentioned in lectures is that is exactly the same as 5 choose 2. Okay, which is also, as some people noted, equal to 5 choose 3, which is equal to 5 factorial divided by 3 factorial, and then again divided by 2 factorial. Okay, which you can check is equal to 10. All right. Now, why was that? So we kind of have the idea now that the number of ways I can rearrange these letters is given by this combinatorial thing here. And that seems a little bit different to the way I introduced it in class, because in class I said, well, you've essentially got 5 cards, 1, 2, 3, 4, 5, and we're asked, when we talked about 5 choose 3, okay, we talked about the number of ways to divide the deck. So we got 3 cards on this side, say the first card, the third card, and the 5th card, okay, and 2 cards remaining in the deck, the 2nd and the 4th. Okay, so this previously was ace, king, queen, 4 and 2, and now I've just done it with numbers 1, 2, 3, 4 and 5. Okay, so the number of ways I could split this set of 5 things into a subset of size 3 and a subset of size 2, where I didn't care about the order, I mentioned was equal to 5 choose 3. Okay, and that seems a bit different to this number of ways of reordering B, 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 W, W. Okay, but actually it really isn't. Okay, they're actually the same thing. Okay, notice in this I've got sort of an order. I've got my first digit, I've got my second digit, I've got my third digit, I've got my 4th digit, and I've got my 5th digit. Okay, and what we've done is I've said I've got a bucket here consisting of B letters, and I've got a bucket here consisting of W letters. Okay, and what I'm doing is I'm saying that the first 3 digits, 1, 2, and 3, okay, go into the black bucket, and the last 2 letters go into the white bucket. Okay, right. Okay, so you can see that for each way of dividing up these 5 digits into a set of 3 and a set of 4, okay, corresponds exactly to each way of dealing out sort of these 5 cards between 2 people. All right, so also just to note that, you know, notice that if I swap 2 of these letters, a W and a W, okay, it's not going to change the order of the cards, and so really it's the same as I don't really care about the order here either. So swapping a W and a W doesn't make any difference and doesn't create a new list. Okay, which is exactly like with the cards. When we deal out the 5 cards, it doesn't matter that you get an ace, then a king, or a king, and then an ace. All right. So here, for example, in this case, notice that we'd have card 1, 3, and 5 being black, B, 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 and cards 2 and 4 being white. Okay. Alright, so this separation of this set will correspond to that sequence. Okay. Now convince yourself that all the ways of splitting up this set into a subset of size 3 and 2 corresponds to all the ways I can reorder these elements. Okay, so this is exactly the reason why those are sorts of the same things. A number of ways I can put 3 labels on top of these 5 letters that are black and 2 labels that are white is exactly this kind of reordering concept. Okay, right. So I'll just kind of quickly reiterate the things that I did in lectures. Okay, so how many words can you make out of the letters for a ballad? Okay, and again the concept's the same. All right, we could think of it this way: that I've got letter 1, letter 2, letter 3, letter 4, letter 5, and letter 6. Okay, and I have to decide. All right, which letter here, which the first, the second, the third, the fourth, the fifth, or the sixth is going to be a B. Okay, there's just one B, and I've got 2 A's. Okay, so I've got to decide which 2 letters are going to be A's, right? And I've got 1 letter, okay, that's going to be a D. Oops. And then finally 2 letters that are going to be L's. Okay, so notice if I gave, for example, the first digit to be a B, the second here, and the 5th digit to be an A, okay, the last digit, digit 6, okay, to be a D, and the 3rd and 4th digit to be an L, okay, that would correspond exactly to the ordering where we got a B, A, L, L, A, D. Okay, so you can imagine we're kind of dealing out the digits. We give 2 to B's, we give 1 to B, 2 to A's, 1 to D, and 2 to L. Okay, work at all the ways we can split up in doing this. That'll give me all the ways. Oopsie, sorry, that should be a D. That'll be all the ways I can rearrange these letters. Okay, now someone asked me afterwards. Okay, so notice, so notice this gives, as I described in class, a kind of multinomial. We've got 6 factorial ways of rearranging these 6 digits. Okay, so then I have to divide by, well, 1 factorial for this set, 2 factorial for this set, 1 factorial because this set is of size 1, and then 2 factorial for this set because it's of size 2. Okay, so I'll end up with sort of 6 factorial divided by 2 factorial, 2 factorial, and I'll just check my answer. So this is 180. Okay, right. Someone asked sort of why isn't the answer 6 factorial? Well, think of it this way. 6 factorial gives me all the ways I could rearrange these digits. Okay, but notice if I kind of swap the 2 L's here, it's not going to change the word. Okay, so if I swap the 3 and the 4, okay, so I got a 4 then a 3 rather than 3 then a 4. If I was ordering these out in sequence, it wouldn't make any difference. Okay, so we've a little bit overcounted compared to the numbers of ways of reordering 6 items, because 2 of them are sort of the same. All right, so we need to divide by these kind of 2 factorials in order to deal with that. Okay, right. So this was the other question I did next. We had a box that has 12 numbered balls inside. So we've got some balls 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, 8 of the balls are black. Let's suppose it's just the first 8. 4 of the balls are white. Let's suppose it's the last 4. Okay, and we're going to take out 5 balls from here. Okay, and now I sort of separated this question into 2 bits. One which is about sequences. Okay, so where we say we get these numbers coming out in sequence, and this is about samples. We just kind of get given 5 balls, let's say, all at the same time, and it doesn't really matter what order they came in. Okay, I always find it personally easier to deal with in sequences when things come in order, but that's, you know, both kind of work, and hopefully we'll kind of see that by the end of this question. Okay, so the first part says find the number of sequences that are of size 5. Okay, so let's do that first. Right, so that is where we're imagining that we kind of reach into this box, pull out 1 ball, okay, and then put it down, okay, in the sort of number 1 slot. Then we choose another ball, and then we put that down in the number 2 slot, okay, and then we pick up a 3rd ball, put that in the number 3 slot, and do that for 5 balls, okay. So here we're sort of caring about the order of those first 5 balls as they come out, okay. So as I mentioned in class, there are essentially 12 things that can happen for the first ball. Then you've got 11 balls left in the bag. Take one out, there's 11 things that can happen. Okay, now you've got 10 things left in the bag, so 10 things the next time. And then 9, and then finally 8. Okay, and that's the number of ways that you can take 5 balls out of a bag of 12 if you care about the order, which was first, which was second, which was third. Okay, all right, and you can notice that that is 12 permutation 5. Okay, and you can check in your calculator that should be 95,040. All right. Okay. So now, how about the number of samples of size 5? Okay. So here, for example, we could be given ball 1, then 2, then 3, then 4, then 5. Okay. Or we could have been given out of those 5 balls by ball 5, and then ball 4, and then ball 3, and then ball 2, and then ball 1. Okay. When we're doing that, we don't really care what order the balls arrived in. We just care that we got those specific 5 balls numbered 1 to 5. Okay. So in that case, essentially what we're doing is we've got sort of our digits 1, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we can imagine we're kind of putting a label on the things, okay, that arrive, okay, and are dealt to us. Okay, so it's a number of ways. We could think of this a bit like the black and the white balls. It's a number of ways we can choose which ones were dealt. If I put a spot on top, if I don't put a spot on top, then they're not dealt to us. Okay, so again, that corresponds to me constructing a set, okay, of size 5. Oops. Okay, those are the 5 balls that are dealt. Oopsies, sorry. And the balls that are not dealt or not taken out are the remaining ones: 2, 4, 5, 7, 9, 11, and 12. Okay, so what we're doing is we're dividing it into the set of things that have been taken out and the set of things that have not been taken out. Okay, and when we get in that kind of situation, we look at combinations. Okay, so we've got 12 combination 5. Okay, which is also equal to 12 combination 7. Okay, you can do the calculation for what that is, and you're going to get 792. Okay, right, so that's just another way. So here we sort of care that we get a 1, then a 3, then a 6, then an 8, then a 10, and here we just care that we get 1, 3, 6, 8, 10, but we didn't care exactly which order they came out of the bag in. Okay, all right, now let's look at part C. Find the number of sequences with 3 black balls and 2 white balls. Okay, so let's have a look at that. So we've got 1. Okay, so it's a little bit of a trickier one, this one, like I say. Let's consider the situation where we get a black ball, a black ball, a black ball, a white ball, and a white ball. Okay, and let's count the number of ways that that can happen. Okay, so the number of ways we get 3 black balls in a row and then 2 white balls. Okay, so we said that the first 8 balls are black and the last 4 balls, let's say, are white. Okay, so there are 8 things, okay, 8 ways I can take out the first ball and it be black. Then there are 7 ways I can take out the second ball and it be black. And then there are 6 ways that I can take the third ball and it be black. Okay, now how many ways are that I can take out the 4th ball and it be white? Now remember, there are 4 white balls in the bag. Okay, so there's 4 possibilities here, not 5, 4 possibilities. Okay, because there are 4 white balls in the bag. Okay, and then finally 3 for the remaining 3 white balls. After taking one of those 4 out, there's 3 left. Okay? Now, that gives one way that I can get 3 black balls and 2 white balls. That's the situation where I get exactly 3 black and then 3 white and then 2 white, sorry. But other things could count, you know. So equally we could have white, white, black, black, black. Okay? And again, there'll be 4 ways that the first ball is white, 3 ways that the second ball is white, okay? 8 ways that the third ball is black, because there's 8 black balls in the bag, and by this point we haven't taken any black balls out. Okay, then 7, and then 6. Okay, it's exactly the same number. Okay, but a different combination where we've got 2 white and 3 black. Okay, and we could have everything in between. Okay, and how many things are in between? How many of these sequences do I have? Well, I've already told you up here. I've written out a list of them. Okay, so we've got everything from black, black, black to white, white, white. Okay, so everything from black, 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 white, white, white down to white, white, black, 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 and there are 10 different combinations in between. Okay, so between here and here, there are 10 of these sequences which all have this number associated with them. Okay, so notice the number of ways of getting 3 black and 2 white in a sequence is, well, 8 times 7 times 6 times 4 times 3 times 10. Alright? And what was I really doing the calculation for here? Well, I've got 8 permutation 3 times 4 permutation 2 times 5 choose 2. That's really the calculation I was doing there. Okay, so I've got 3 things in order, okay, taken from a bag of size 8, followed by 2 things in order from a bag of size 2, and then I can jumble them up any way I like, and the number of ways of jumbling them up is 5 choose 2, because of the answer I gave earlier. Right? So the total I get here, okay, is, I've got the sum here, I've got 40,320. Okay? Right, now let's do the same question, but now we're going to do it for combinations. Actually, it's a little bit easier in this case. So find the number of samples that I can take where there's 3 black balls and 2 white balls. Okay? So let's have a look at that one. Okay? So let's think about it again. We've got our numbers 1, 2, 3, 4, 5, 6, 7, 8, which we've assumed are all black. Okay, and then 9, balls 9, 10, 11, and 12, which we've assumed are all white. Okay, we said we're going to take 3 things, okay, from the black balls, and then 2 things from the white balls. Okay. So we can sort of divide this into 2 parts. Firstly, how many ways of me taking 3 things out of this list? Okay, where it's 8, choose 3, because we've got 8 things. We're choosing 3. A set of size 3 out of this. Okay, and 8 choose 3 gives me the number of ways of choosing 3 items out of this list of size 8. Okay. Okay. Then I can look at how many ways of me of taking 2 things out of this list of size 4, which is 4, choose 2. Right? And notice for every way I can take 1 thing out of here, I can choose 4 choose 2 things over here. Okay? So once I've fixed that I'm taking a 2 and a 5 and a 7, there are 4 choose 2 combinations that I can take out 2 from this list. Okay? So the number of combinations over here is 8 choose 3, and for each of those there's 4 choose 2 ways of taking out the white balls, and so the total is the multiple of the 2. Okay, which you can check for yourself is 336, just doing the calculation there. Right? Finally, which I didn't cover in class, I can ask the question, given balls are chosen at random, find the probability of getting 3 black balls and 2 white balls. Okay? So we've got a box that's got 12 balls in it, 8 are black, 4 are white, we take out 5, what's the probability that 3 of them are black and 2 of them white? Okay? Well, there's 2 ways of answering this question. One in terms of permutations, as we've used in A and C, and one in terms of combinations, as we've used in terms of B and part D. Okay? And both of them work. Okay? So, one way to think about it, so we could say the probability of 3 black and 2 white. So one way is it's the number of sets of where there's 3 black and 2 white, 336, divided by, okay, the numbers of sets of size 3 that I can take out, 792. Okay, so number of ways I can take a set of size 5, where 3 are black and 2 are white, okay? Or I could think of it the number of ways I could take out in sequence, okay? 5 cards, so 9,540, okay? Divided by the number of ways that I get 3 blacks and 2 whites in sequence, okay? So 40,320. And notice I've written them both the same here, okay? And that's true because if you do the calculation for both of these, you get the same number. About 40% of the time, 42% of the time, you're going to get 3 black balls and 2 white balls, okay? Notice those are 2 ways of answering the same question. One in terms of combinations and one in terms of permutations, okay? Both ways work, okay? One, we look at how many sets or, you know, that we get out of here, and the other, so how many samples we can take, and the other is how many sequences, right? So the point I'm trying to get across is sort of both work, okay? The issue is you've got to be careful to know which one you're working with. Do you care about the order that things come out in, or do you not care about the order that things come out in, okay? And there's all manner of mistakes that people make. I regularly make them as well, I'll have to admit. But you have to try to be sort of careful to specify the problem as you go along. I personally like to think in terms of permutations and think about the orders that things are happening in. I find it's more specified, so I prefer to work this way. Obviously, the issue is that you can see that the kinds of numbers that I'm dealing with are much, much larger here than you would be in terms of combinations. Okay? Anyway. Right, so that's to give you a bit of an idea about those. Okay? A lot of the questions you get when we talk about the number of samples, we're talking about combinations. So that's kind of a key word to look out for in kind of tests and things like this. Right? Okay, here's a further question that I'd like to cover. All right. So we've got a 64-bit string, okay? And that's a sequence of 64 zeros and ones. So you can imagine I write like 1, 0, 1, 1, all the way 64 times, okay? The question is, how many 64-bit strings are there? Okay, so imagine for this kind of sequence of zeros and ones, I want to write down all of them and then store them on a memory disk somewhere. Okay, the question is like, how big does that memory disk have to be? Okay, and then a question we have is, what are the number of strings where half of the digits are ones and half of the digits are zeros? Okay, and then finally, what is the probability that a random string has half ones and half zeros? Okay, so there are some questions on your tests which are kind of this nature. They're not necessarily for bits, but they're sort of yes, true, false, whatever, yes, no, this kind of thing. All right. So, how many 64-bit digit strings are there? Well, there are 2 choices for the first digit. Okay, and then, well, there's 2 choices for given those. There's 2 choices for the second digit. Okay. And then given those, there's 2 choices for the next one, okay? And I just keep on multiplying 64 times, okay? Okay, so now we've got 2 to the power of 64, okay? We can write down what that is. It's 1844473070395511616. Okay? So it's a bit like 18 times 10 to the power of 18, roughly. Okay, so it's a ginormous number. Okay? So if you think about it in terms of what we'd need, remember that, you know, we've got 64 numbers to store, okay, and there's this many of them, okay, so I'd need sort of 64 times 18 times 10 to the 18 to store this, and you can work out that that's about 1.2 billion terabytes. Okay, so I'd need about 1.2 billion 1 terabyte hard drives to store all of the 64-bit strings. Okay, so it gives you an idea of like how massive things can get, particularly when it comes to coding and computers and things like this. Okay, so it gives you a real sort of picture that even if we've got something as short as sort of 64, okay, I could quite easily write down 6401 digits, okay, but very quickly we're getting to something where I'd have to spend an enormous amount of money on hard drives, enough to compete with Dropbox in order to store all of those digits. Okay, right, anyway, next thing, okay, what is the number of strings? Okay, by string I just mean a sequence of zeros and ones, where half of the digits are ones and half of the digits are zeros. Okay, so let's have a look at that. Well, what we have, okay, is we essentially have a list, okay, of 64 digits, okay, 1, 2, 3, okay, up to 64, right? So think of that being the first position, the second position, the third position, all the way up to 64th, okay, and then some of them, half of them, I want to have a 1, okay, and the other half I want to have a 0. Okay, so think of me putting a dot on top if it's going to be a 1, that digit, and if there isn't going to be 1, there's a 0 there. Okay, so again, it comes down to one of these kind of combinatorial questions where we're saying we're sort of splitting the deck in half. Okay, we've sort of got a deck of 64 cards, okay, and half of them have to go into the ones pile, and half of them have to go into the zeros pile. All right, so again, we're getting to the situation of the ways of choosing 32 items out of a list of 64. Okay, so we're going to get 64 choose 32. Okay, and this, when you get in the calculator, is about 1.8 times 10 to the power of 18. Okay, so we see again an absolutely ginormous number. So that gives you an idea that these combinations also get extremely large very quickly. Okay. And then finally it says, what is the probability the random string has half ones and half zeros? Okay, so let's assume I get a random number generator, okay, and I generate a 0, 1 string, okay, what is the probability that half of the digits are ones and half of the digits are zeros? Okay, well, so the probability that we get half ones, well, is the number of strings that have half ones, which is 64 to the 32, divided by the number of strings, okay, which is 2 to the power of 64. All right, and you find that the answer to this is about 10%. So we've got about 18 divided by 1.8 divided by 18. Okay, so we get an answer that's about 0.099. So about 10% of the time, if you choose a random string, about half of the digits are ones and half of the digits are zeros. Okay, so quite a sizable fraction actually of this ginormous 1.2 billion terabyte database consists of things where half the digits are ones and half the digits are zeros. Okay. Another thing to note about this, which will come up a bit later in the course, is notice if I take 1 divided by the square root of pi times 32, I get about the same answer. All right. That seems a bit cryptic at this point, but you can actually approximate quite well, okay, by taking this 32 here, taking its square root, times it by pi, and again approximately the same number there. Okay. It's useful that such a large number of digits are ones and zeros. For example, if you look at like QR codes, okay, so remember these kind of boxes which are kind of a bunch of black and white tiles, okay, and you can scan it with your phone and you look at a website with it and all the rest of it, okay. You can see in there you can store an absolutely ginormous amount of information, okay. That is because, you know, even if we took a 64-bit QR code, we've got about, you know, we've got 18 times 10 to the 18, this many different, say, websites you could go to or whatever. So yes, the amount of information you can store in there is absolutely massive. Okay. The other thing is it needs to be balanced. So you can't have a QR code that's all black. Okay, you need about half of the digits to be white and half of them to be black in order for a phone to pick it up. Okay, and so that's why it's important that this bit is true as well, that a reasonable proportion of those codes have half white, half black. Okay, all right. So you know this is kind of important. Both these types of questions come up in your computer test, but also they're useful for computers. Okay. Anyway, one more question that's sort of similar style to your computer test. Okay. Find the number of ways of choosing. Okay. So find the number of ways 3 girls and 3 boys can be seated in a row. Firstly, so that there is a group of all girls and then a group of all boys. And then second, so that no boy sat next to another boy. Okay? So let's answer that question. So part I, we essentially need girl, 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 then boy, boy, boy. And how many ways are there of doing that? Okay? Well, there are, so we've got positions 1, 2, 3, 4, 5, 6. Okay? And then there are, well, 3 girls that can go in the first position. Okay? Then 2 remaining, because we already placed one of the girls in the first position. And then 1. Okay? Then we go to the 4th position. Now we've got to have a boy, because we've finished all the girls. Okay? And there are 3 that can go here. Then 2 that can go here. And then 1. Alright? So essentially we've got 6 times 6, which is 36 ways of organising. So there's a group of all girls and a group of all boys. Okay? Next, we want to kind of have so that no boy is sat next to another boy. Okay? So let's think about that. So a little bit trickier. So let's imagine we start with first girl, boy, girl, boy, girl, boy. Okay? So, well, how many ways are there of arranging so we get girl, boy, girl, boy, girl, boy? Well, there are 3 girls we can choose from for the first position, followed by 3 boys we can choose for the second position, because we've not used any boys in the first position. Then 2 for the third position, because we already used 1 here, then 2 here, then 1 here, then 1 here. Okay? So exactly the same as the first part. 3 times 2 times 1 times 3 times 2 times 1. Okay? So then the question is, how many ways can I arrange these G's and these B's, okay, so that no 2 B's are set next to each other? Okay? So essentially what you can notice is we've sort of got this floating G here. I could move that here, alright, or here, or at the front here, okay, and then there would be no 2 boys sat next to each other. Okay, so it's sort of, I can essentially move this G into this girl slot into each position here. So we end up with kind of like G, B, G, B, G, B, B, G, G, B, G, B, okay, B, G, B, G, G, B, and finally G, B, G, B, G, B, G. Okay? And so I've gone through all the combinations of the different ways of having girls and boys. Okay? So no two girls no two boys are sat next to each other. And if I wanted to extend this out, I could do this in a more combinatorial way, looking at a number of ways of sort of boy-girl pairs and things like this. Notice we sort of have to have pairs of B's and G's together, and then we can kind of move things around like that. Okay, but ultimately what it comes down to is we've got sort of 36 times 4, okay, which is going to give me like 144 or something like this, okay, and then that'll be the correct answer for that question, right? All right, so that summarises another 4 questions which are similar to your computerised tests on Friday, and there's the additional examples that I've also covered in the other videos in this post.